Greetings, intrepid explorers of the cosmos and intellectual adventurers. Today we embark upon an extraordinary intellectual expedition, delving into the profound implications of Albert Einstein's most celebrated and deceptively simple equation, E=mc². This monumental formula, a cornerstone of modern physics, not only elucidates the fundamental relationship between mass and energy, but also illuminates the potential pathways for humanity's audacious dream of interstellar voyaging. It is the theoretical bedrock upon which our aspirations for traversing the vast cosmic ocean are meticulously constructed. At its conceptual core, E=mc² articulates the principle of mass-energy equivalence, a revolutionary insight positing that mass and energy are not disparate entities, but rather interchangeable manifestations of the same fundamental cosmic substance. This profound equivalence implies that a minuscule quantity of mass possesses the inherent capacity to be transmuted into an absolutely colossal amount of energy, primarily due to the astronomical magnitude of the speed of light squared, represented by c². The speed of light, an immutable cosmic constant when squared, becomes an unimaginably immense multiplier, amplifying even the most negligible mass into an energetic behemoth. To truly grasp the immense power encapsulated within this equation, consider a hypothetical scenario. If merely the mass equivalent of a common paperclip were to undergo complete and instantaneous conversion into pure energy, the resultant energetic discharge would be comparable in destructive potential to a substantial nuclear detonation. This vivid illustration underscores the extraordinary energy density inherent within even the most prosaic material objects, awaiting liberation through appropriate physical processes. It is this latent power that beckons us toward the stars. The profound implications of E=mc² for the future of space travel are nothing short of transformative, offering tantalizing glimpses into propulsion systems that could redefine our cosmic reach. Our current technological prowess already harnesses the principles of nuclear fission, a process involving the deliberate splitting of heavy atomic nuclei to generate electrical power in terrestrial reactors and to propel certain conceptual spacecraft designs. While undeniably potent, fission reactions yield significant radioactive byproducts and offer a comparatively modest energy release per unit mass when juxtaposed with more advanced nuclear phenomena. It represents a foundational yet ultimately limited energetic paradigm for deep space exploration. The true energetic frontier, however, resides in nuclear fusion, the celestial process that powers our sun and myriad other stars, wherein lighter atomic nuclei, typically isotopes of hydrogen, are compelled to coalesce into heavier elements like helium. Fusion promises an exponentially greater energy output with a dramatically reduced environmental footprint, potentially enabling spacecraft to attain a substantial fraction of the ultimate cosmic velocity, the speed of light. Mastering controlled fusion propulsion represents a monumental engineering and scientific endeavor, yet its successful realization would fundamentally redefine the parameters of interplanetary and even interstellar transit. For the ultimate expression of E=mc²'s power, we turn to matter-antimatter annihilation, a process representing the most exquisitely efficient energy release theoretically attainable within the known universe. In this extraordinary interaction, every single particle of mass, both matter and antimatter, is entirely converted into pure energy, achieving a staggering 100% mass-to-energy conversion efficiency. This unparalleled efficiency makes it the theoretical pinnacle of propulsion systems. To contextualize this immense power, consider that the complete annihilation of just 1 gram of antimatter with 1 gram of ordinary matter would unleash approximately 180 terajoules of energy. This colossal energetic discharge is roughly equivalent to the explosive force of 43 kilotons of TNT, a truly staggering amount of power from an almost imperceptible quantity of fuel. The formidable challenge, however, lies in the incredibly arduous and prohibitively expensive processes required for antimatter production and its subsequent, meticulously safe containment. Despite these extraordinary energetic possibilities, the universe imposes an immutable speed limit, the speed of light itself. As a spacecraft endeavors to approach this cosmic velocity, its relativistic mass experiences a dramatic and exponential increase, consequently demanding an exponentially greater expenditure of energy for each incremental acceleration. This fundamental relativistic effect dictates that no amount of energy, however vast, can ever propel an object with mass to or beyond the speed of light. Nevertheless, this relativistic constraint does not entirely preclude interstellar travel. Rather, it refines our objectives. We can realistically aspire to achieve significant fractions of light speed, perhaps ranging from 10 to 30% of c. Attaining such velocities would render interstellar journeys, spanning light years, feasible within human timescales, potentially completing voyages to nearby star systems within a few centuries. It transforms the seemingly impossible into a challenging yet conceivable engineering endeavor. An intriguing and often counterintuitive consequence of traveling at near light speeds, derived directly from Einstein's theory of special relativity, is the phenomenon of time dilation. At these extreme velocities, time itself demonstrably slows down for the intrepid traveler when compared to the temporal progression experienced by observers remaining stationary on Earth. This means that while a journey might feel like a decade for the crew, many more decades or even centuries could have elapsed back home. For instance, an interstellar voyage undertaken at 90% of the speed of light, lasting 10 subjective years for the onboard crew, could translate into several decades having transpired on our home planet. This relativistic effect presents a fascinating paradox. It makes extraordinarily long voyages survivable for the astronauts themselves, preserving their biological age, yet simultaneously introduces profound complexities for communication, intergenerational relationships, and the very concept of a return journey to a vastly altered Earth. Humanity's imaginative and scientific endeavors have already yielded several compelling conceptual designs for interstellar propulsion, each attempting to harness the principles of HMC2 in various ingenious ways. Project Orion, conceived in the 1950s and 60s, audaciously proposed using sequential nuclear bomb detonations to propel a massive spacecraft, a testament to early, albeit controversial, thinking about extreme propulsion. It was a bold, if environmentally problematic, vision. Later, in the 1970s, Project Daedalus emerged as a sophisticated design for a fusion-powered starship, meticulously engineered to achieve 12% of the speed of light, targeting Barnard's star. This detailed study showcased the immense engineering challenges and potential rewards of fusion propulsion. More recently, the ambitious Breakthrough Starshot initiative envisions deploying laser-propelled microsails capable of reaching 20% of light speed to journey to Alpha Centauri within approximately 2 decades. This project represents a paradigm shift towards miniaturized, ultra-fast probes. In summation, EHMC2 is not merely an abstract scientific formula. It is the indispensable theoretical key to unlocking the colossal energy reserves required for humanity's eventual deep space peregrinations. While the engineering challenges, encompassing fuel production, energy containment, and the profound relativistic effects, are undeniably immense and multifaceted, this equation provides the definitive roadmap. It is the foundational principle that guides our transformation of audacious science fiction into tangible scientific fact, propelling us toward an interstellar future